Hello, everyone. Thank you for joining me this evening, or actually this morning, for all of our attendees. Thank you. Today we will be discussing the wireless sensor networks for agricultural applications in Asia, specific to Asia Pacific Rim. We'll cover applications, factors to consider. I am Richard Rodriguez, Product Marketing Manager for Outdoor and Agricultural Products, a recent addition to the team at Onset. I actually joined the team there about just a little over a year ago. Also on the line, we do have the Channel Manager for the Asia Pacific region, Caroline. So if she will be helping me out, assisting with any, in the event that there are any technical difficulties, if I drop off for whatever reason, she'll be, you may hear her voice. So hopefully that won't be an issue. Onset has been manufacturing, for anyone that is new or unfamiliar with Onset, we have been manufacturing sensors and data loggers in the United States since 1981. So we are in no way a newcomer. We've been around for close to 40 years and are known for reliability and the durability of our products, which are used to monitor environmental conditions all over the world and are trusted to endure harsh conditions and provide reliable data when needed. So, you know, if you're looking for anyone looking for a partner that has been around and will be around for a long time, that is us. So before we get started, the agenda, I'll start off with discussing a few challenges in agriculture, which really are shared or general globally, and then we'll move on to HOBOnet, or Onset solution to sensor networks for agricultural type applications. I'll dig in and really spend most of the time today on these applications. We'll discuss a few growing applications and then non-growing applications, and we'll end with factors to consider when selecting a wireless sensor network. In total, this should take about 45 minutes and leave us a few minutes for any questions you may have at the end. If you do have any questions, please feel free to enter those in your control panel. At the bottom of your control panel, you'll see a drop down for questions, and I will do my best to address those at the end. Also, this webinar is being recorded and will be available for viewing in the next 24 hours or so. And for challenges, really challenges for farmers or growers really tend to translate, I find, globally quite equally. Of course, climate impacts that can lead to crop losses. Here in the northeast of the United States, cold weather, for example, at the wrong time of year is one major enemy for a lot of the attendees tonight. I expect, or actually, sorry, this morning for you guys, extreme rain or high temperatures may be more of a concern. Environmental regulations, of course, many governments add additional regulations in order to minimize the impact of agriculture on the environment. Meaning those regulations tends to create new challenges. Changing consumer preferences. Many times, consumers themselves want products that are more fresh or are grown more sustainably. And then another trend is lack of availability or aging of labor. Looking at statistics globally, the average age of farmers or farm labor is increasing and is really over the age of 60 by quite a wide margin in most parts of the globe, which makes it difficult to keep up with the growing demand of farming. So what are we really discussing here in terms of field monitoring system? What is a field monitoring system and why should you care? Basically, it is a system of tools consisting of both hardware and software components, perhaps remote communications also, that enable us to monitor the environmental conditions in a field. For farmers, this is the ability to monitor microclimate conditions on your farms and understand how these conditions change from point to point. It is the ability to know what your crops are experiencing on your farm based on the direct measurements of your tools rather than based on weather data from an airport, which may be 20 or 30 kilometers away or more. And why do this? Basically, it comes down to time and money. These tools can save growers precious time, and the right data can also, at the right time, can also help improve your bottom line. And at Onset, just 2 or 3 years ago, launched a solution for microclimate monitoring known as HOBOnet. This is our wireless sensor network solution that provides users the ability to easily monitor different conditions at several points in the field. I'm excited to talk to you today about it because we've recently added a new option in terms of communication frequency, which makes HOBOnet now suitable in more regions across the globe, more specifically in the Asia Pacific Rim. So now HOBOnet offers two distinct options for APAC with our 921 megahertz hertz option covering Taiwan, Thailand, and Malaysia, and the 922 megahertz option covering Australia and New Zealand. And what benefits can you expect from a wireless sensor network such as HOBOnet? So the right field monitoring system can help you reduce costs associated with irrigation by allowing you to water only based on plant demand rather than a set schedule. You can protect crops and workers from excess temperatures, so whether it be excess frost, cold, or heat. You can set up real-time alerts to let you know where there is this risk. It helps you determine when environmental conditions create high risk for pests. A lot of these pests, whether they be insects or fungi, they occur when there are certain sets of temperature or humidity levels, and you can monitor those to understand when you may be at high risk. They can also help you plan your spraying activities for these pests. So whether it be helping you apply pesticides only when conditions are appropriate, or helping you avoid applying them when conditions don't warrant their application, so they save you time and money in that way. It will also help you avoid spraying when conditions may make it dangerous to apply, so such as high wind conditions, which we'll cover in a few minutes. A system such as HOBOnet can also help you record historical environmental activity data for compliance and claims. So again, if you're spraying pesticides, you may want to record the fact that that when you did that, wind conditions were appropriate, so that you to ensure that you were meeting guidelines. You can also monitor multiple points quickly. So one farmer, one farm manager can monitor a very large field from a tablet while sipping coffee and planning his day. You can also easily monitor your fields with less people because all of the information you need comes to you. And now getting into applications. So we'll start with lychee. Like all fruits, the development of lychee is tied to temperature cycles and really water at different points in the plant cycle will influence the amount and quality of the fruit. So really directly impacting the bottom line here. So understanding the relationship between water and temperatures is important for profits. So in growing lychee, some of the research I read through seems to indicate that drought can be used to control shoot growth and hence flowering in areas that have dry periods during the autumn or winter. So a lot of the what I understand is that moderate droughts after flowering can increase fruit production, though these gains are at the expense of fruit size. Severe droughts at this time reduce fruit set and yield and can lead to fruit splitting. Well-grown trees can extract water down to 1 meter to 1.5 meters within the soil. So really this reduces, looking at all this, putting all this together, really indicates that there's an opportunity to reduce the amount of watering applied in commercial orchards for lychee. So because of this, measuring soil moisture at multiple depths through the root zone may provide an advantage to growers that will help them view how water moves through the soil. So rather than feeling the soil, using visual cues of the soil to understand determine if water may be needed. A device that reaches deep enough within the root zone can tell you whether or not there is still water within the root zone for the tree. Moving over to oil palms and rubber trees, which I put these two together as they seem to found quite a bit of research that seemed to indicate some similarities in where they grow and how they grow. Typically a lot of they grow in regions with varying topographic positions. So you have a lot of low-lying plantations, which are often prone to flooding compared to upland sites. So trees within the same region really seeing very different conditions. Research seems to indicate that long-term flooded conditions may lead to reduced plant water uptake, which means opportunity for increased damage from frequent manual latex extraction. It also facilitates the entry of fungi and leads to reduced productivity and vitality of the rubber trees. So because of this, growers may want to be able to quickly monitor soil conditions or to understand whether there is an excess amount of water in certain parts of a plantation so that they may be able to address that. Now moving on to orchids. Orchids are one of the more some of the most valuable potted flowering crops commercially produced throughout the world. And one of the big reasons for this is because they have a long flower life, so it makes it appealing to buyers, but also to retailers, which can have them on the shelves for a good amount of time, but also because it's easy to schedule the crop flowering base to meet specific market dates. So orchids require exposure to certain temperatures for a certain amount of time in order for flowering to begin. So they're often grown at temperatures that are too high for flowering to begin in order to keep them ready to ship and only flower when on a specific marketability date. So for example, a holiday that may be coming where retailers believe they can sell a lot of them. The grower wants to keep as many of these flowers from flowering or plants from flowering up until those are absolutely needed. So these temperatures vernalization, so flowering temperatures, these really depend on species. So an example of this is actually the most common type of orchid, the Phalaenopsis. actually only grows flowers when temperatures are at 25 degrees Celsius or below. So they're typically grown at temperatures above 28 degrees Celsius. So because of this, it may be important for someone growing orchids, especially indoors in a controlled environment, to monitor those temperatures. We have some customers doing similar types of activities here in the U.S. Where they use our MX or Bluetooth devices to help them track the amount of chilling hours or the amount of hours required for vernalization or that flowering to occur. And they tend to do this so that they can plan on having crops ready for shipping ahead of these holidays, such as Thanksgiving and Christmas. Then we also have HOBOnet, which is a great candidate to help with this, which will do that tracking, really record that, collect that data, that temperature data for you, but will also enable you to monitor these conditions remotely and add the ability to set temperature alerts. So say someone growing orchids in a greenhouse, they can remotely check on their growing conditions, and if there's a problem with either the air conditioning system or any other types of controls, and the temperature either becomes too low or too high, an alert can be sent by text message or email to alert to that problem. Moving on to rice and rice cultivation, major factor for crop success is water level, keeping that water level high during different points of crop development. At times, high water level is required in order to maintain higher temperatures in the root zone to protect vulnerable roots. Given the size of many rice growing operations and challenges with labor, we recommend remote monitoring for water level, which there are several ways to do this, to check on water level remotely. But we're actually working with a university in the United States, which is currently using HOBOnet with soil moisture sensors and temperature probes to study the effects and the opportunities to reduce water usage in rice crops grown in Arizona. So this is a study looking to find ways to reduce water usage. It's a conservation type of study. So soil moisture and temperature are being monitored remotely, and the water level is being cut, or the amount of water sent into the field is being cut, these temperatures of the root zone is being monitored to determine how far or how long water can be kept away from the crops, again, in an effort to conserve water. Wind conditions in rice may also be critical for planning harvest. Fair over sustained high winds may lead to rescheduling or pulling in harvest dates. So we recommend considering adding wind sensors with HOBOnet, which can provide data on average wind speeds, peak and sustained wind speeds, and can provide alerts based off of these metrics to notify anyone that winds may become a concern and a harvest should be planned. So one common topic that we covered in the past few applications was soil moisture. Soil moisture sensors can help, of course, in many different applications, help with determining crop water needs and help improve irrigation practices or water usage by improving really your ability to plan based off of actual needs as opposed to a fixed schedule or anything that may have been done in the past. Soil moisture data can be viewed for planning estimating when, for example, you'll have to water crops next. We've come across situations quite often where someone wants to know whether or not they can spray pesticide, for example, but and need to know whether or not they can hold off on watering for long enough to not dilute the spray application. You can also set soil moisture thresholds to alert you, again, by phone or email, to the need to pay attention to soil moisture. There are two main types of soil moisture sensor measurements, volumetric water content and soil water potential. So soil water potential is a measure of tension or stress of a plant required to pull water from the soil. So rather than telling you how much water there is in soil, a soil water potential sensor will tell you how much of that water is available, how easy it is for a plant to pull that water. Because of that, it's actually a favorite technology for farmers compared to the volumetric water content. Volumetric water content, on the other hand, will just tell you how much of a percentage of volume of soil is water compared to mineral soil. And they are related. Tension. They're related in the sense that they really depend on the type of soil that they go into. When I mentioned that growers prefer the soil water potential sensors, it is because it is agnostic, or it doesn't care what type of soil you're in. It will just give you the same, one reading will tell you what the stress is on a plant, rather than its counterpart, the soil water content, which tells you how much water there is, but you don't really know how easy it is for that water to be absorbed by a plant. And the way I explain this is, if you think of different types of soil, they have different sizes of particles in them. They have different amount of spaces for water to move through. So if you think of sand, grains of sand are quite large, which means that there's a lot of space between these grains for water to move through. And it's almost like for a plant to pull water from sand or sandy soil, it's almost like you drinking water out of a cup with large pieces of ice, large blocks of ice. Quite easy, compared to something like clay soil, where those particles are a lot smaller, they're much more tightly packed, there is less room for water to move, and it's more like drinking a slushy, or you crush ice really tightly, really small, tight packet, and fill that cup with juice. Try to drink that through a straw, and it will be a lot more difficult. An example of this, if you look at the right-hand side of your screen, we show you a comparison between sand soil and a clay soil, and you'll see that for each type of soil, you require a different amount of water in order to provide the same amount of water available to plants. So here, for example, we see the optimal amount of water for a crop, meaning at the very top of this, it's called field capacity. Field capacity indicates how much water field soil can actually hold before it becomes saturated and muddy. And this is indicated by a negative 20 kilopascal, which is a negative number for pressure. For sand, you really only need 10% of the volume of that to be water, where compared to clay, you need 50% of that to be water in order to. So you need a lot more water in clay to provide the same benefit to the plant than that you would see in sand. Looking at HOBOnet soil moisture sensor options, we cover both types of measurements with wireless sensor options. For easy point-to-point comparison, again, where if you have a farmer and they're going to be looking at soil moisture at different points, and they don't want to worry about the different types of soil type, the HOBOnet T21 is a great option for that. We also then have the T11 and 12, which are very robust volumetric water content sensors. These are meant for long-term deployments in different types of soil. The T12 also offers electrical conductivity measurements. So if you're wondering or want to look into how different composition of soil may change as you add apply different chemicals to the soil, this will be a good option. Also, because of the placement of the temperature sensor in the T12, the T12 is a great option for anyone doing indoor growing and not using mineral soil. So if you're using a non-mineral media to grow indoors, the T12 is a great option. We actually published a white paper recently on how to calibrate this sensor for those types of applications. And then I did mention when talking about the Lychee that you may want to, in some applications, measure soil moisture over multiple depths. I'll give you a quick preview. We do have a multi-depth soil moisture probe coming in the next month or so. So stay tuned. And then if you're just looking for a very simple and economical solution, we've got the EC5s and 10HS. Now moving away from growing applications, we'll talk a little about compost. In composting, heat during composting is an important factor, one of two very important factors. So heat and moisture within the pile are crucial to ensure that proper composting is taking place. So by measuring heat in the pile, you can predict the decomposition rate or oxygen content within the pile and the overall health and efficiency of the composting operation. It helps to predict when the pile may need to be churned to introduce more oxygen into it, when the pile is finished with its hot cook cycle, and if you have effectively killed any pathogens or weed seeds that may have been present in the feed stocks. Monitoring is an important aspect to streamlining and creating a stable process and workflow to get a predictable and consistent result through each cook, improving the overall efficiency in the operation. We have several options that are often used for measuring temperature within the compost pile, depending on the need for remote or local monitoring. If local check of the pile temperature is sufficient, we have our MX2300 family are great options because they have long cables that can reach well into the pile, and an employee can just download or check on the temperature with a mobile device, such as a cell phone, and ensure that everything is okay. And for a larger operation or remote operation where someone may want to check on this remotely, HOBOnet is also a great option for that. Looking at moisture, ensuring that correct moisture management is key to successful composting as well. So if the moisture in the compost is too low, the microbial processes needed to break down the organic materials are slowed, and the compost doesn't reach the needed temperatures. If the moisture is too high, basically water fills the pores in the compost, which then removes the oxygen the microbes need. Then this process becomes anaerobic, and the compost pile begins to smell bad, and then it becomes basically an air pollution hazard. So to ensure that compost pile is okay, I've read that the recommended range for moisture content is about 45 to 65%, where 50% to 60% is optimal. However, there seems to be quite a bit of challenge or misunderstanding and how to properly monitor moisture in a compost pile. Basically, it comes down to what percentage of moisture do you need to measure. Are you measuring volume-based or mass-based? Are you starting for doing a percentage of the wet compost or based off of the dry compost? So it seems that based off of what I've come across, that the numbers given for the guidelines indicate that it's you should be measuring a percentage of wet-based gravimetric water contents. So basically, it's the mass of water divided by the mass of wet compost. So how do you do this? The only direct measurement would be done with a balance in an oven, which is really not practical in most applications. Then you've got probes like the HOBOnet T11 soil moisture sensor, which is again a volumetric water content sensor. So you would have to convert the readings that our sensors give you to really understand how that translates to gravimetric water content. And we can provide you. I can actually refer anyone interested to these instructions, but it's actually quite quick. I won't spend too much time on it. But an example is if you use a T11 probe to measure the volumetric water content, and say you get a reading of 21%. You'd want to fill a bucket with compost and find the weight of that compost in the bucket, and say that comes out to be 1,500 grams. And you then determine what the weight of that same bucket full of water would be, and say that would be 4,000 grams. The ratio, so basically the weight of the water divided by the weight of the compost will give you 2.7. That's your ratio. You multiply that by that 21% reading that you got from the T11, and that's how you get you come to 57%, meaning that you are within the optimal range for composting. And I cannot take credit for this. This I got from our partner at the Meter Group, manufacturer of the sensors we actually use. And moving on to a slightly different part of agriculture, animal transport. Common application for our data loggers is actually transport of livestock to different markets, for example. And in warm climates, transporting livestock, such as chickens, may mean that several animals that are layered over each other, you have several rows of cages. It may create a very hot environment for a lot of the livestock that may be positioned in the middle of the pile. So we have some users using a Bluetooth temperature data logger to monitor the temperature there. And then at each stop, the driver can quickly confirm or check on the conditions for those cages. And if certain temperatures are met, they can determine whether or not it may be needed to rotate the cages to avoid losing any livestock during transportation. Very common application for HOBOnet wind sensors is pesticide spray drift. I know at least in some countries, pesticides are highly regulated, mostly because pesticides are actually designed for very targeted application. They're not meant to just spray all around. Most crops, most plants are susceptible to dying if they come in contact with pesticides, unless they're actually bred genetically to resist those pesticides, which makes it tricky when you may have a farm adjacent to a crop that is not that cannot come in contact with that pesticide. In these cases, it's very important to monitor spray drift, or actually not just monitor spray drift, but avoid spray drift. There are two ways that drift can occur. There's particle drift and vapor drift. Particle drift happens when basically small droplets travel long distances because of high winds. So say you're spraying, it's windy, and those pesticides end up on your neighbor's farm instead of on your farm. To avoid this, at least here in North America, the regulations state that you should not spray, you should only spray when wind speeds are between 3.8 kilometers per hour to 12.8 kilometers per hour. So that's the recommended range. Wind speeds below that 3.8 kilometers per hour may indicate that there's a temperature inversion, which I'll cover in a minute. Wind speeds higher than that will just simply blow away the spray and lead it off well beyond the buffer zone. Vapor drift occurs when products volatilize or evaporate due to high temperatures and then move off target. So typically this can occur with a lot of these sprays at temperatures above 30 degrees Celsius, especially on days where the relative humidity is low. Temperature inversion, basically when warm air is trapped above a layer of colder air down below, which keeps air from mixing. It basically creates this, a blanket of still air hanging out right above the crops. And what ends up happening is when you spray, instead of the spray just settling on the crops and doing what it's supposed to do, it just kind of hovers above the crop like a mist, and then any slight breeze can carry that off site. In order to protect or help with spray drift, there are two recommendations here. One, using wind speed and direction sensors with HOBOnet, which you can use to ensure that conditions are okay prior to spraying. And then you can also set alerts to send someone a text message in the event that wind speeds pick up and increase or change direction. And instead of blowing in a favorable direction, begin blowing toward I don't know, a neighboring farm or school where those pesticides should not be drifting to. Then temperature and relative humidity points to help with ensuring that the sprays don't volatilize or there is no temperature inversion. So the recommendation here that that a farmer would install a temperature point at about the spray boom height, and then another at about 3 meters high to ensure that the temperature, that there is no temperature inversion. All right, and that covers it for applications. We'll now move on to factors to consider when selecting a sensor network. So the first really point to determine is whether a single station is needed or a single measurement point or versus a sensor network. So say if your customer or your farm resembles something like this on top, where you've got a nice plain landscape with no changes in elevation. This really becomes quite easy to monitor. You wouldn't expect that conditions would change much from one point to another, such as temperature, wind, sunlight exposure, even soil moisture. That won't change much. On the other hand, if you're looking to monitor something like down below, where you've got big changes in elevation and the sun's going to be facing crops from different directions, it becomes much more critical to measure or monitor different points, because you would expect that temperatures will fluctuate from top to bottom. Sun exposure again, the amount of water settling down at the bottom of a hill will be much higher than what crops see up at the top. Then ease of deployment, very, very important point. There are different ways to deploy, and for the first subtopic here will be actually making the connection between a wireless sensor and your central station used for communications. Likely the easiest, actually what we decided to go with for HOBOnet is the push of a button, much like pairing devices with a router at home or a Bluetooth headset. You push a button on two different devices, they go into pairing mode, they find each other, and they're connected. It really doesn't get easier than that. Other devices require the use of a mobile device app, which will allow you to search for a nearby device and then use the app to pair that device and configure it. Some devices, some sensors require the use of dip switches, where you position buttons in different positions to get them to pair, similar to what you would see in like a garage door opener. And then other more complex systems require programming. So basically you would need hopefully have someone available to you familiar enough with programming that can really do these more complex setups. But for ease of deployment, in most cases, you probably want to find a solution that uses one of the first two options. So within ease of deployment, mounting, you'd want to consider size and weight. Of course, a smaller, lighter device is easier to carry out into a field and mount. You want to consider the power source. Does it run off of battery power, or does it actually have a solar power option, or can you just plug it into a wall? So you can avoid having to replace batteries every so often. How do you mount it? Are there integrated mounting provisions, such as we like to provide options for screw mounting or using zip ties, which makes it easy to position on a post and move around if needed. Software, another major factor to consider is software or user interface. How easy and intuitive is it to configure? How easy is it for you to use? What kind of information will it display? Can you set up information that's most relevant to you? Can you share the data with others? How easy is it to access that data? Can you share the data with other programs? So can you export the data easily to use it to manipulate it in your preferred method? Can you have set up automated sharing to FTP sites or email? Can you access it through third-party web services? Is it also, you want to make sure that it's compatible with your preferred device, mobile or desktop device. So is it can you access it through an iPhone or an Android phone? Is it compatible with both PC and Mac? Wireless coverage and its adequacy for your application and location is very important. Again, I mentioned earlier in this webinar that we just added a wireless option for Thailand, Taiwan, and Malaysia. So are those wireless frequencies appropriate for your geography? Also knowing what type of application it's going into, you want to know, will I have enough range so that I can position the sensor far apart enough? What kind of frequency does it use, and will it be compatible with the actual crops that I'm growing? So a lot of most manufacturers will list a wireless range based off of line of sight, which provides a consistent way to compare a device to another device in terms of range. However, those don't really give you a feel for what will happen when there are plants obstructing that line of sight. Plants, trees, different vegetation, hills, buildings. These will all reduce that wireless range. So to give you an example, we decided to use a 900 megahertz wireless signal, which we found to be less attenuated by vegetation than a 2.4 gigahertz signal. 2.4 gigahertz is quite common. You'll see that around quite often. It seems to have great range, but as soon as you introduce some foliage, that signal dies down rather quickly. Still within the wireless coverage, what kind of network does it create? One common type of network is a star network, in which all sensors communicate back to one central station, which then communicates your data to the internet. This type of network limits the range of your sensors to the radius around that central station, depending on the maximum communication distance between the sensor and the central station. With a mesh network, the sensors can communicate through each other to get back to that central station. The advantage here is that because you can relay the information from one sensor to the other, you can extend your network of sensors out much farther from that central station. This makes it very easy and affordable to increase the coverage of a single central station and a single data plan. So you have the option to use other sensors or repeaters to extend out farther and farther. Then your longest range, or your farthest radius from the central station to that farthest out point is determined by the maximum number of hops permitted from sensor to sensor, and the maximum distance between devices. So to give you an example, for HOBOnet, the maximum range, or the range from one sensor to another, is between 450 meters and 600 meters, depending on mounting height and obstructions. We also have a maximum number of hops of 5 hops. So you can jump a signal from one sensor to another 5 times. This means that your farthest distance from the central station to the farthest out sensor will be between 2,250 meters and 3,000 meters radially. So at full diameter, you can cover up to 6,000 meters. And we do have a self-healing mesh network, so that the network will actually find another path. So one sensor will find another path to get to the central station if, say, an animal or farm equipment or bad weather knocks out one specific device. Alarm notifications and response. Can you actually create alarms? Can you set these alarms so that you can get notified of any critical conditions by phone or email? Are these alarms done in station versus web-based? So in-station alarms basically means that the sensor itself will determine that a critical condition occurs. So say you want to monitor for flooding, the sensor will determine that water height reaches a certain level and immediately trigger an alarm response. compared to a system that uses web-based alarm, where it would have to wait for the next phone call to take place for the software to determine that a critical condition occurred and to relay that alarm. You would want to know if anything, you'd want to be able to turn anything on or off. So if you get an alert, a critical alert, do you want to be able to, say, trigger an irrigation system? If so, you would want to look for a system that offers a relay output. Then maintenance of historical data, understanding how long your data is stored and available to you for your use, you know, and what types of uses you would have. Why would you need to recall that data? Do you think you would want that to be available to you often, or just in case something comes up? You know, and with HOBOlink, your data will be maintained for as long as you maintain your account. Scalability. You'll want to consider how easily you can scale your sensor network in the event that you may consider, you know, starting off slow, but or starting off small with just a handful of sensors, and as your operations grow or your experience with sensor grows, you may become more interested in adding additional capabilities. That's something that you will want to think about upfront when making that initial investment. And total cost of ownership. You'll want to account for initial costs. How much does the equipment cost up front to purchase? Are there any installation costs? And then annual recurring costs. What are the cellular or web-based service plans? Typically, you would expect that a data plan would be required for completely remote wireless stations or gateways. Are there any additional costs per node or sensor? Some manufacturers charge recurring fees for equipment. So as you add a sensor, you add a recurring fee. To be clear, that is not our practice. We charge for a data only. If you need cellular connectivity, there is a charge for that data plan. Outside of that, there is no other recurring fee outside of the purchase of the equipment. For maintenance, are there any calibrations or checks needed? How much will it cost to replace a sensor? You expect that every sensor has a limited life. You'd want to know what it will cost to replace. And again, future expansion costs, assuming that as you become more familiar with the system and the power of the sensor network, you may want to expand that. You'll want to consider what the cost or the ease of having that flexibility will be. And finally, who owns your data? Is data for your use only? Is it used by a third party? I have come across some providers, typically really a couple of European providers that offer very low entry cost services, but then use your data for other forms of revenue to really subsidize the cost of that equipment. In our case, Onset does not use your data. We don't share your data. We don't look at your data for any particular reason. We just store it for your use. And with that, we conclude the presentation. I'll consider any questions you may have. So affordable and reliable connections are an issue on many properties. So do you offer compatible extended range Wi-Fi solutions? No, the only options we have, we have a standard cellular option, and we do have a Wi-Fi and Ethernet option, but those you would have to be in proximity to a facility or building with that connectivity. We don't have an option for extended Wi-Fi. Can the HOBOlink sharing the data to own customer cloud? Yes. we do have several customers that do that. You can set up an automatic sharing of data that will go from HOBOlink to your own service. We do have an API. We do offer an API so that you can integrate HOBOlink data with any other service you may need. And it seems to be it for questions. I'll give everyone another 30 seconds for if anything else comes through. Well, with 5 minutes to spare, I'd like to thank everyone for your time. I hope it was worth your while, and hope to talk to you all soon. Have a great day.